and welcome back for what I'm sure to be is a very stimulating second keynote talk. I'm very pleased to introduce my new colleague, Dr. Jonathan Cannon, who received his PhD in mathematics from Boston University and has done postdoctoral work at Brandeis and MIT. His research focuses on rhythm and timing in action and draws on his musical background. He has extensive training as a violinist and is still a member at a distance of the award-winning Boston-based klezmer band Ezekiel's Wheels. When not using music to study brains or using his brain to study his own music, he's also a co-founder of Flying Leap Games. This company, which I learned about recently when I wrote to Ani Patel asking for some interesting dirt on introducing Dr. Cannon. Apparently his company offers many award-winning games, including Wing It, Penguin Pin, and my personal favorite, How to Lose a Guy in 1 DM. I'm not even sure what that means, but it seems like it's a great game. While he loves games, he's also quite serious about his research. Since arriving at McMaster, he's founded the LIVELab, looking at models and experiments in timing, rhythm, and entrainment, and really enmeshed himself in the research life of our department. His growing team's work focuses on a number of areas of rhythm and timing, most recently the role of the brain's motor system in extracting and anticipating rhythmic structure in music. I'm looking forward to hearing what he's discovered most recently, so please join me in welcoming Dr. Jonathan Cannon.
Well, we're having a few minor little issues here, but I can at least tell you a little bit about my talk. This is going to be called Rhythm and Groove in the Bayesian Brain. My background is in math originally, so I don't come at this with tremendous experimental skills, none of the really impressive work you've seen previously from EEG, from fMRI. And so what I try to bring to these questions about rhythm instead is a level of precision and just trying to use models to see specifically what is it that we're talking about when we talk about music cognition. And unfortunately, one of the most boring things to see in a talk is mathematical detail. So I'm walking a fine line, trying to really wring what I can out of the mathematical details while at the same time not putting everyone to sleep. So I'm going to do my best on that front, but I do hope to convince you that actually making detailed models and looking at the details of what we're trying to talk about is worthwhile and can give some real insight into the healthy and disordered brains and how we understand music. All right, and we may have to wait just a moment. Okay, here we go. So first of all, just right to the chase, what is the Bayesian brain? So this is a theory. It's closely related to predictive processing that as Peter was discussing, but I'm coming at it from a slightly different direction. The idea of the Bayesian brain is that the brain is in the business of representing things, representing important hidden bits of the world. So here we've got a situation where we can't really see everything happening because of the tall grass. And here we've got some kind of representation of an object, or in this case, we're going to say a lion that's hidden in the grass somewhere. And so we've got a representation of that in some form in brain activity. But the Bayesian brain goes further and says that this representation should be probabilistic in some way. There's some kind of uncertainty associated with this representation. And so we don't just know where it is, we have some sense that is to a greater or lesser degree uncertain. And it builds up this representation by incorporating observations into these ongoing estimates. And so here we've got an observation based on a rustle in the grass in a particular place. And we're going to incorporate that observation into this estimate, which is now changed of where the lion is. It became tighter and moved over to the left. And the way we incorporate those observations is informed by an implicit understanding of how hidden states, like where the lion is, generate observable data. And so we've got this internal model, which may be learned or may just be an implicit understanding that we have, that lions in a particular position tend to create rustles right around where they're standing. And so we've got this generative model of how rustles in the grass are created by lions. And we can use that generative model to then take our observation of a rustle and use it to update our distribution or our representation of what's happening. An important point that I'm going to come back to a little later is that when we do this update, a according to a Bayesian formulation of this kind of updating rule, what we're going to do is we're going to minimize the surprisingness of the observation plus the surprisingness of the update. And so if I hear a rustle somewhere completely different, that's surprising data. I'm going to need to update my sense of where that lion is. But that if I completely decide that it's teleported over here, that's a very surprising update. Whereas if I decide that the lion's still in the same place, well, now the observation itself is really surprising because I just heard him rustle over there. And so I'm going to need to strike some kind of balance where I update my sense of where the lion is, but I also am doing it in a way that's conservative and doesn't create a really drastic change in my representations of what's going on in the world. So I'll come back to that. And linking this up with predictive processing, as Peter was describing, these representations can then be used to anticipate upcoming observations. And we've got this model of how lions create rustles. And so if we have an estimate of where the lion is, we now have predictions of where the rustles are going to be. And so we get prediction for free when we're doing this kind of reasoning in our brains. Okay, so finally to music. What is hidden? Well, there's ordinarily no lions hidden in musical rhythms, but there are things that are consistently not directly observable about musical rhythms, but that we can infer and try to represent in our brains. One of them is the current tempo. So here, I'll play my favorite rhythm of all time, and we'll see how this sounds. Let's see, do we have anything coming through? You know what, I'm going to take a cue from Peter and just give you a... Now, once I've repeated this once or twice, not only do we have predictions about when the next event is going to happen, but we have predictions about where our pulse is going to happen. We have predictions about where we would move if we were moving. And in order to make those predictions, we need to have something in our brain that's representing the tempo, the speed at which this is playing out. We can flexibly do exactly the same thing at a different tempo. And because we're making these very precise predictions, we must have some kind of representation of the speed at which this is going that's flexible. We've also got some kind of representation of the instantaneous phase of an underlying cycle. So the one cycle underlying that kind of rhythm that we experience viscerally is the beat. And I'll do this one with my foot, of course, because otherwise it would be very difficult. So this part down here is something that if I'm not stomping it with my foot is still represented in my own experience and therefore must be represented in some way in the brain. And so here's a nice little animation. There we go. Yeah. So you can think about the phase of the beat as where that clock is pointing. We've got some continuous thing that's unfolding in our brains that tells us where we are in that cycle and where events are going to happen. And then the last thing that's hidden is metrical structure. So one way to think about that is here I've illustrated the subdivisions of the beat. So when this beat clock is pointing downwards, we kind of expect an event. And when it's pointing upwards, we really expect events. Events are very likely on the beat and a little more occasional off the beat. And so these are all things that we're able to put together in our brains just by listening to this rhythm and have some kind of ongoing representation of which we can then use to make predictions. An important note here is that two of these things, the tempo and the metrical structure, change occasionally. In certain fancy music, or if somebody starts rushing or something, we're going to see changes in the tempo or changes in the meter. Whereas the phase of that ongoing cycle is completely dynamic and that clock keeps ticking and ticking and ticking and turning. So we've got two different kinds of representations that are happening here. One of them is representing something that is fairly static but occasionally changes, and one is something that is moving. So I'm going to focus first on something static, and what does it look like when the brain is representing metrical structure? So this is the model that Peter illustrated. I'm going to try to provide a little more detail about it. So in this model of meter representation and meter inference, we are listening to a music or to a rhythm, and we're trying to figure out, is this rhythm, does it represent some underlying structure? Is it being generated according to underlying rules that correspond to a 4/4 meter? Or is it a total random set of events that are being pulled out of a hat completely randomly? Our generative model, our picture of how this rhythm is getting generated, is that we may be moving between those two templates at any given time. There's some probability that we're going to switch from a 4/4 meter to nothing or randomness, and some probability we would switch back. And we're going to maintain a distribution. Remember, these representations are all probabilistic. They all have a certain amount of uncertainty. And so we're going to maintain a distribution over these two possibilities, probability of one, probability of the other. And we're going to evaluate and incorporate every observation of a sound event using these kinds of update rules. And so here's the rhythms that Peter was illustrating earlier, low, medium, and high complexity. And here we can see what happens over time to that distribution over those two possibilities. Up at the top, we've inferred that we're doing the 4/4 template. Down at the bottom, we've got this null template. And here we can see for low syncopation, we remain very confident that we're listening to something that's generated in 4/4. Here we have some lapses because of the syncopation, but ultimately we basically decide we're in 4/4. And in this very high complexity rhythm, we lose track of the 4/4 and just say this must be completely random. Now, all of this depends on parameters. All of this depends on the way I formulated the model. But I think it's the idea that we're maintaining this distribution, that something in our brain is representing that distribution that's important. So I'm going to return to this model in a bit. But moving ahead, I want to also show what it might look like if we were to model our representation of the underlying phase of a cycle. So in this case, this thing is moving. And to keep track of a moving thing in a way that actually represents our uncertainty about it, we need fancier algorithms than just trying to keep track of a distribution over two possibilities. One that is perfectly suited to this and is, in a sense, the most natural probabilistic way to do this is called the Kalman filter. The best example of that I've found is how we keep track of where cars are on GPS. So if you've seen your little dot here and you've seen a circle around it, that actually represents the level of uncertainty about the car's position. And so roughly the way that the GPS algorithm is doing this is it has an estimate of where the car is at one moment. It also has an estimate of how fast the car is driving. And at the next moment, it's going to come up with a predicted estimate of where the car is with a certain level of uncertainty. And it'll get a measurement from a satellite. And that measurement is also a noisy measurement. And so then it's going to try to integrate those two things by weighing its prior or its sense of where the car is, or its prediction of where the car is going to be against its measurement and incorporating those together into a more certain estimate of where that car is. So that's the Kalman. Where we are in the cycle of the beat, we can assume that what we're maintaining is just some kind of distribution over where the beat is. And for simplicity, we can make it the simplest of all distributions, the Gaussian distribution that just has a mean and a variance, some level of uncertainty to it. And this is a distribution on the circle. So it's a distribution over the possible phases we might be at. We might be about to experience the next beat. We might be just after a beat. We might be halfway in between. So in this model of trying to keep track of a beat, we are also expecting events at a particular phases of the beat. And so here I'm representing something that looks a little bit like a quadruplet subdivision of the beat, where at a particular phase we really expect an event. Halfway in between we expect events, and at the 1/4 and 3/4 mark we kind of expect things as well. Oh, here, yeah, I'll use a laser pointer there. Yeah, so there's where we really expect events. And we have those expectations with a certain degree of precision. So we, for instance, we may have variable auditory delays that make it so that when we hear a sound, it doesn't always happen at exactly the same moment that it was produced. Obviously, we've got a certain constant delay, but then there's also a certain amount of variability. And so we may not be absolutely precise about where those sounds are going to occur. And the sound clarity also may play into how precisely we expect the timing of a sound. My favorite analogy to try to explain this model that I put together is if you're listening, you're watching a runner run around a circular track, but it's dark. And so you can't really see where the runner is, but you can listen. You have a sense of where he is, an estimate, a representation of where the runner is on the track, and conveniently you left some bells. So whenever you hear a bell, now you've got a good sense of where that runner is, or at least it's as good as the precision of your bell placement. And so, but then in between, after you hear that bell, you become progressively more uncertain about where it is again. So thank you for bearing with me through this elaborate model of how we keep track of the cycle of a beat. I'm now going to try to convince you that this is actually a valuable way to see this problem in the brain. So here's what this model looks like if you animate it. This blue thing represents our distribution on the phase of the beat, which is wrapped around a circle here. And when you hear a sound event, that distribution updates to incorporate the observation. So there is our sound event. It happened a little bit later than we expected, and so the distribution had already said, oh, we must have passed the beat. There was no event there. But then the event happened, and our distribution updated in order to show that, wait, no, that must be where the beat is. We can plot that over time. Here's the distribution wrapped around the circle up and down, and here it is moving over time. And when an event occurs, it updates and becomes more certain. And here's this in action, actually treating a real rhythm. This is the rhythm I was playing before, dup, bup, 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 bup. And you can see how it starts out very uncertain. After one event, it becomes somewhat certain about where the phase of the beat is. After another, it becomes more certain, and we start to resolve that uncertainty. Conveniently, there are experiments in the literature that allow me to fit these expectations to actual human data. Just very briefly, those experiments are ones in which people are listening to metronomes or subdivided metronomes, and there are small shifts in timing, and we see how that affects their prediction of when the next beat is going to be. And so this then could be a reasonably precise picture of what might be happening to our representation of the beat. We can see the uncertainty decreasing whenever an expected event occurs, and increasing in between events. And this model is robust to timing perturbations, because if a whole set of events are shifted slightly in time or delayed, when the offbeat events happen, we become a little bit more certain about what's happening. And when our precisely expected on-beat events happen, we get this resetting of the beat phase that really tells us exactly where we are in the cycle. You can read out of this model to see how our predictions about events will unfold over time. And so here we can see that if we discontinue the rhythm at a particular moment, we actually still expect a few beats afterwards, though our expectations are going to fade over the course of multiple beats when we don't hear any events to reinforce our sense of where the beat is. And here's a fun example of how this model can actually provide some intuition for something that really happens in the brain. So here we're listening to a syncopated rhythm. I'll try to tap this one, though I haven't actually practiced this. Dum, bump, dump, bump, 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 bump. No, wait, one moment. Dump, bump, 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 bump. Hey, what a mess. So it's not an easy rhythm. But it's one in the category of something like this, where we've got a lot of events that are not lined up very carefully with the beat. And if this model has a sufficient degree of certainty about how, if it doesn't lose its confidence in where the beat phase is too quickly over time, it can keep track of the beat through that rhythm. But if we change the parameters a little bit and it loses confidence, then we see something we see in actual human participants, which is that it starts to align those events with the beat and interpret the rhythm in an alternate way. It gets this resetting effect. And so this is something that the model does, and we actually can now attach some intuition to how humans might lose track of a beat and start to align it differently. I mean, I guess one of my favorites is the rhythm I was playing before, which is, and if you're listening to that, you can put the beat somewhere else, and you can keep track of this one, but then you kind of lose it. You switch back to the other way of hearing it. And that's because this balance between our certainty about our own timekeeping ability and the precision with which we expect things at certain phases of the beat balances out one way or the other. Okay, so we can start to build more complex models out of these pieces. For instance, one that is keeping track of the phase while also trying to infer the metrical structure. This is just one quick slide on this picture. If you simulate those two processes happening in parallel, you can do this really fun thing where you can show some results from iterated reproduction experiments, where people have shown that if you're from a particular culture that listens to certain rhythms a lot, then when you hear those rhythms, you'll reproduce them faithfully. And if you hear your own tapping, you'll reproduce the rhythm faithfully again. But if you're from a culture that doesn't have those rhythms, you tend to reproduce it in a way that's sort of biased towards the rhythms you're more familiar with. And if you're asked to reproduce what you just tapped, you'll do it again. All of that happens as a result of the interaction between keeping track of the phase of the beat and inferring what the rhythm is that you're listening to. And so here you can see this two possibilities. Are we listening to a 1-1 ratio rhythm or a 2-1 ratio rhythm? And as that unfolds, you can see that we've decided that, in fact, we're listening to a 2-to-1 rhythm, but there's a lot of uncertainty about where the beat is. Whereas if you're somebody who has a prior that there could be a 4-to-3 rhythm, then as you listen, you become more certain that, in fact, it's that rhythm you're listening to. And your sense of where the beat is becomes much more precise. So by putting these pieces together, we can start to build these pictures of how inference during music unfolds in the brain. Now, this is where I find it gets really fun, because just describing how that happens is exciting enough, at least if you're into the math. But we can start to use these models to get insight into rhythm and movement. So most humans are pretty good at synchronizing movement with a beat, for which beat perception is necessary, but not a sufficient thing. This is something a little bit more complicated. And sometimes we feel compelled to synchronize movement with the beat, as Peter was describing, groove or pleasurable urge to move to music, plum. And here's where I want to draw some insight from something that initially seems completely unrelated, but is one of my favorite experiments, which is a rubber hand effect, where you are putting your hand in a certain position, and either because of an actual rubber hand that you can see or because of virtual reality, it looks like your hand is a little bit displaced from this particular position. And when you do that, I mean, people have shown that you start to feel ownership of the hand, but what's especially interesting is that your hand will start to generate forces that move it in the direction of the image. You can see here, if your hand is displaced to the left, you see some forces in the negative direction. If it's displaced to the right, you see some forces in the positive direction. This has been shown and reproduced. And there's two key pieces of insight that I think are really important to understanding music and movement. One of them is that movement in this situation arises in order to reduce sensory conflict. So the surprisingness of multisensory data is getting reduced when your hand, the feeling of your hand, the proprioceptive experience of it, starts to line up with the image. And second, well, the reason that there's a sensory conflict in the first place is because the brain has conflated the externally generated image, or the rubber hand, with your own hand. So you've got this sensory conflict that's happening because you've identified these two things as coming from the same source. We identify with the stimulus, and then we move to relieve the dissonance. So to formalize these two insights, over here, recall that Bayesian inference, which we were talking about at the very beginning, in the Bayesian brain, minimizes the surprise of the observation plus the surprise of the update. Well, when you're moving, you're not necessarily updating things in your internal representations, but you are updating what you're actually observing. And so the idea of active inference is that movement arises in order to do the same thing, to minimize the sum, but it only gets to affect the surprise of the observation. And so we move to just reduce the surprisingness of what it is we're experiencing. And this we can loosely call self-other integration. The brain is identifying externally generated sensation as if it arises from the self, as long as that explanation seems to fit. So the rubber hand effect I'm going to illustrate, and then I'm going to take us over into music and movement using the same exact structure. So in the rubber hand effect, we've got two input sources that inform the same estimate of hand position, which is a self-other conflated estimate of the hand position, where we're trying to estimate where that hand position is, treating the rubber hand and our hand as if they are the same. And one of them is the image of the hand, which is generated externally, as it turns out. And the other is our proprioceptive experience of the hand, which is self-generated. And active inference makes movement arise to reduce the unexpected misalignment of the proprioception and the proprioception and the estimate of where the hand actually is. So, how could this inform synchronization with rhythm? Well, suppose that what we have here is not an estimate of the phase of an ongoing beat in a rhythm we're just listening to, but is a self-other conflated estimate, where we are conflating the phase of our own movement and the phase of the thing we're listening to. And we just have one model that describes both of them. Well, once we've done that conflation, we are now able to take rhythmic input in order to inform our estimate of the beat phase, and the feedback from our own tapping along to inform the estimate of the beat phase. And the active inference process is going to have us move to reduce the unexpected misalignment of our own tapping and the phase that we expect that it should be at. So this becomes actually synchronizing or generalized synchronization, tapping along even with something where we're not necessarily synchronized with a metronome, but we might be tapping off beats, we might be tapping somewhere else, we might be tapping a particular rhythm. Nonetheless, we're synchronizing because there's specific phases at which we expect our taps to occur, assuming that this estimate of phase is actually describing the cycle of our own tapping. So if we try to model this, the first thing we need to do is actually treat our own motor feedback like another rhythmic input, as if we've conflated our own movement and the feedback from it with the metronome. And so this could be our auditory input from our own tapping, or just the tactile or proprioceptive input. And it's going to inform that estimate of the phase of the beat with its own level of precision, which may be determined by how much we're paying attention to our own motor feedback versus the metronome or the rhythm we're listening to. And then that estimate of phase through active inference is now informing the cycle of our tapping, such that the perceived beat phase tends to align with the timing of our tap. So I put together a sort of proof of concept model of this. One prediction that this model makes is that ongoing tapping should be somewhat insensitive to perturbations in metronome timing, because my own tapping feedback is competing now to entrain my sense of rhythm with the thing I'm listening to. Whereas if I start tapping immediately following some perturbation in the rhythm, I should make a large adjustment, because my own motor feedback is not competing. And it turns out that if you flash back to 2002, that's already been upheld. I love formulating things as predictions when they've already been proven. But this is a Bruno Rep experiment showing exactly that. And so now we can try to explain this by saying, well, in this situation where we've got an ongoing tap, we are entraining ourselves in the same way that if we were listening to two metronomes at the same time, our sense of the phase of that cycle would have to strike some kind of compromise between them. Another prediction is that if we delay some of the feedback from our own tapping, then as we entrain to that feedback, that should then act just like delaying a metronome. And our own tapping should get delayed just by hearing our own feedback delayed. This is a slightly weird prediction. It comes from that one of those arrows in that active inference diagram where we are treating our own motor feedback as if it's telling us about the phase of the rhythm. And then we're aligning our tapping to the phase of the rhythm. It turns out that has been upheld not only during continuation tapping, when I'm tapping not with a stimulus, but also even when I'm tapping along with a metronome. If I see or if I hear the auditory feedback from my metronome or from my own tapping delayed, then you'll see that the next interval, my next tapping interval, is extended, as if I had listened to a slight delay in the metronome that I was tapping to. And so we really are treating the experience of tapping and the thing we're listening to as examples of the same thing. They're informing the same exact model and having similar effects on our own movement. And the final prediction is that if for some reason we are now paying more attention or just have reduced attenuation of our motor feedback, then our response to metronome timing perturbations should be reduced as our own motor feedback starts to outcompete the metronome. And so this is that in a simulation. We see that if you increase the attention or precision, the extent to which our own motor feedback is weighted as we make these estimates of beat phase, then we see significantly reduced responses to perturbations in rhythm. And then now we go over to data from autistic participants. Autistic participants have shown reduced EEG attenuation of self-generated sounds, as if they're more sensitive to the auditory effects of their own movement, and increased influence of auditory feedback on the timing of their speech, as if, again, they're more sensitive to the exact timing and feedback from their own movement, and a reduced response to metronome timing perturbations. And so I'm trying to link these things together by saying that maybe all of this comes together in this idea of active inference, and in particular, the idea that our own motor feedback is entraining our sense of rhythm. I've been calling it self-entrainment. So this is a way in which this kind of precise model where we start to actually produce these mathematical representations of all the things we're talking about can start to give us insight into what's happening in cases of neuroatypical brains. So now switching over to this groove effect, the pleasurable urge to move, I'm putting exactly the same diagram up here, only in this case, we've got an estimate of meter happening in the brain. And we are conflating the information about meter that we get from a rhythm we're listening to with the information we get about rhythm from our own motor feedback, from our vestibular and proprioceptive feedback, the experience of moving. And then, according to this rule of active inference, our movement will be motivated in order to reduce the surprisingness of what we're hearing. And so if we're hearing something that is a little bit surprising, that doesn't perfectly fit our schematic model of how rhythms unfold, then we're going to be motivated to move in such a way that we get data that makes it less surprising what we're listening to. And so now this is coming back together with what Peter Voice was talking about. And of course, this picture is motivated by his work, this predictive coding model for understanding rhythmic incongruity. And so we're now back to this simple model, trying to decide between two different possible templates according to which the rhythm is generated. And here we've got the fancy rhythms, low, medium, and high complexity. And here we've got the same things. This is what we would be experiencing if we were moving along with the rhythm in a metronomic way, the way that we usually dance to something. And this is the diagram Peter has already shown. But hopefully at this point, now that I've gone over some of these details, it's a little clearer that what we're doing here is trying to move in order to create a set of observations that are now less surprising if we assume that they are coming from the same generative source. So if we assume that my movements and their feedback are generated by the same metrical structure that the rhythm I'm listening to is generated by, through the self-other conflation, like in the rubber hand, then we see that only for the medium syncopation rhythms are we motivated to add that metronome and create less surprising data. Now, how is this actually valuable, this insight? Well, for starters, the same thing can be applied to a larger corpus of rhythms. We've started looking at Fitch and Rosenfeld rhythms, and we're seeing the same inverted U shape that Peter was describing before in urge to move. If we replace this with a model in which you're inferring the phase of the rhythm and the meter at the same time, we see exactly the same inverted U shape. And we can apply this to Parkinson's disease. So Peter showed these plots, which were collected from these experiments with people in healthy controls over different ages and people with Parkinson's. What he didn't show was that we actually fit these models to each individual participant. And there were two key parameters that we were trying to fit. One of them was how persistent the meter was, which is to say how unlikely we were to switch from one to the other or back. And the other parameter was the contrast, which was how strongly we expect beats or events on the beat rather than off the beat. The spikiness of this template. And when we fit these two parameters, what we see is really not very much difference in metrical contrast between people with Parkinson's and without, and not much difference with age. Although there is evidence that in order to get good fits, we do have to fit this parameter to each individual. And this is disease severity for Parkinson's. But when we look at this meter persistence effect, we see really substantial differences between the healthy controls and the Parkinsonian patients, and a substantial change over the progression of the disease. And so not only are we seeing that people with Parkinson's or more advanced Parkinson's don't have the same urge to move to syncopated rhythms, but we're actually seeing that what is affecting them might be related to something, their internal model of rhythm persisting, and that if we're inclined to quickly lose our model of meter, quickly lose the sense that something is truly in 4/4 and just give it up and admit that this might be completely random, that would create exactly the types of changes that we're seeing in Parkinson's. All right, so as a takeaway, and it looks like I'm gonna have a little bit of extra time, but as a takeaway thought, I'm arguing here that the Bayesian brain formalism allows us to get specific about the way in which we parse rhythmic structure. So rather than just thinking that that we have some internal model of music, we're able to start breaking it apart and saying like, okay, we've got an internal model of when events should happen relative to a certain ongoing meter, and a model of what the meter is at this particular moment. We've got a model of where the phase of the beat is. We've got a model of the tempo. All of those things need to be in some way represented by activity in the brain. And it starts to give us insight into how movement interacts with rhythm perception. So once we've got those details ironed out, we can start to see that movement will naturally synchronize with our internal estimates of beat phase and naturally arise when it will reduce the surprisingness of our estimates of meter and what we're experiencing from the rhythm we're listening to. And finally, it gives us tools to explore rhythm and movement in typical and atypical or disordered brains. And so our proof of concept here is this Parkinson's data, but I'm hoping to take this in the direction of experiments with participants with autism, and also looking into stuttering as well, which shows differences in rhythm perception. And by doing experiments that are informed by these models, I'm hoping to be able to isolate what are the things in the brain, the specific processes and the specific estimates, the specific levels of precision that are changing in order to give rise to the specific effects that we see both across individuals and across conditions.
There you would probably need an extra template that could take care of that, you're actually changing the meter completely. For instance, if you have something that goes over the bar line with a different, a different cross rhythmic
Like the
stuff.
sting example you were playing?
Sorry?
Like the example that you played?
Like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. So this goes over the bar line. This is just dotted eighth notes, right? So there this would be a different one that would be, that would not be the null template, it would be a different meter altogether. So could you have 3 meters in your model, and could you then see whether you would be going directly or via the null template to the other one?
I see. So when you make the transition from one meter to another, how do you get there?
For instance?
Yeah, I don't have a great answer to that. I think there's, but I have thought during the process of estimating beat phase, if we experience a drastic change in meter, we're going to need to reset everything in some way. We need a different phase of the beat, a different tempo, and a different meter. And for that, I think, yeah, I don't have a great answer, but I think, I mean, I guess you could try to do experiments with things like ERPs to see whether deviations in the rhythm as you're making that transition are surprising in light of one template and surprising in light of the other template, or unsurprising. Yeah, I think it would be interesting to ask whether we're taking a route through that transition that goes through total confusion, or whether we've got a more streamlined way of making that transition from one to another. Yeah, so I think, I think that with the modeling setup that I've got right now, I haven't yet done a thorough experiment looking at inferring tempo and meter and phase all at the same time during a transition, because then I think that's what you would have to do to move to a different template. But in principle, yes, the model should do that. I think there's some working out details to do, but yeah, you could watch that occur.
Another question in the back?
So question again about the model. I know in Peter's talk, this 4-against-3 polyrhythm was kind of brought up, and I was just thinking in the context of your model, right, that there's, in that prior plot that you had, you could see very clearly the strong weak, medium weak kind of, peaks. But then with that 4-against-3 polyrhythm, you're going to have the polyrhythm pulses violating all of those expectations. And so how does the model handle that? Because we saw when Peter did his demo that we still have that strong indication that we're still in 4, but we're hearing all of these violations that are occurring at points that are unexpected.
So I think that actually would play out in a very similar way to the syncopated rhythms that we were seeing before. The model, as you're trying to infer the phase of the beat, says that events may or may not happen at each of these subdivision points. If an event happens that is very close to an expected beat point, we adjust timing. But if it lines up better with a subdivision, then we make whatever small timing adjustment we need to align with that. And so this does allow for subdivision structure. And I think that what Peter was also pointing at in subdivisions is that it's really important to pay attention to the subdivisions that are implied by these polyrhythms you're listening to, the subdivision structure. And how comfortable we are with that subdivision structure, and not just the overarching two contrasting cycles. And so I think that the fact that you've got these templates for when you expect subdivisions, and you can move between those templates, I think that takes care of that.
So we have about 4 minutes left for one long or 2 quick questions. Maybe gentleman in the blue shirt over here.
So you going for it?
Hey, Jonathan, I had a quick question about phase of the beat. Are you referring to time feel in the song when you speak of phase of the beat, like how much on top of the beat they are versus down the middle versus behind the beat? Because like some of your great session drummers, they alter that in order to serve the tune. People like Hal Blay and Jim Gordon, etc. And like, for example, on a tune like I Am Woman, right? Jim Gordon on the chorus, of the song, he brightens the time field on the ride cymbal, and it turns it into an anthem, really. And where the real skill is needed is where you pull away that brightness when you go back to a verse, so the audience doesn't perceive you as having dropped the time. So when you speak of phase of the beat, is that what you're referring to?
So yeah, you can model that kind of careful alignment of something. I mean, if you do a more fancy version of this phase of the beat, you've got different templates for different instrumental voices. And so I might expect bass drums to fall at a very particular point, and that might actually define, where I experience the beat. But then I might expect the ride cymbal to fall at these very particular locations over the course of the phase of the beat, or for other instruments just to play slightly early or slightly late. N. Danielson's work showed that depending on your experience and your musical background, you hear the beat in different places when you hear different instruments play at certain times. And you might expect two instruments to play with a slight asynchrony between them, and hear the beat even more clearly when that's the case. And so it's clear that these templates that I'm talking about are to some extent learnable and can be tweaked. And it's possible that they can even live on a continuum where you're moving between, one type of sound and another type of sound. And I think the best example that for my mind at least, is swing ratios, where you're able to hear something as a pretty natural rhythm if it's played as a triplet, or somewhere in between a triplet and a duplet, kind of hard to do with my voice, even harder with my feet. But yeah, I think all of those things correspond to just having these different expectation templates that align with the beat in different ways.
And I think to add to that, you need to take into consideration the timbral qualities of the instrument. I studied with Joe Morello, who was in Dave Brubeck's group since 1987. I worked with him for 20 years. And when I first started studying with him, he told me you have to think of each piece of the drum set as an individual instrument. Mm-hmm. So then, like years later, it dawned on me, I said, from a cognition perspective, like if you're Charlie Parker, you're playing a honkin' saxophone solo, really burning, and I'm Max Roach and I'm behind you on the ride cymbal, all of a sudden I jump to the hi-hat, you're gonna throw something at me. Because if I don't do something to alter either the dynamic level, the time field, or the tempo itself to compensate for the fact that it's an instrument of lesser energy, the audience again is going to say that drummer just dropped the time. You see what I mean? So you have to take into that the timbral qualities of the instrument as well.
Yeah, that sounds like something we should be thinking about. Yeah, thank you.
All right, for our final question, let's turn to Sean here.
Thanks, Jonathan. That was a really engaging talk. Really good ability to translate the mathematical stuff and make it approachable.
Thank you.
I was just curious about what the model would predict or how it would fit to two conflicting streams of information. Like what I was thinking about is sometimes when you're at a live show and you have a delay in the auditory and the visual, how would you, but there's both 4 meter, they're the same meter, but they're augmented. Would, like in an extreme example, if the phase of the auditory was anti-phase with the visual, would your model just resort to the no model, and then you'd have no sense of a beat? But there is a beat, there's just two, I don't know.
So I think maybe a simpler example that may be along the same lines is if you're listening to two metronomes that are slightly out of phase with each other. Maybe one of them's a little noisy or something, but are you hearing them as part of the same stream, or are you choosing one or the other? There was this wonderful 2014 experiment with Mark Elliott et al., where they played two different metronomes and showed that if they were close enough to each other, you sort of took an average between them. Right. And if they were far enough from each other, you kind of had to choose one or the other. Sure. And if this beat phase tracking model is run on that kind of thing, basically the same thing happens. You end up either treating one of them as a subdivision of the first, or ignoring it out of hand based on the model being configured to say that events are allowed to happen at random phases that have nothing to do with anything, just the sort of noise effect. Or if they're both happening near the same time, then you use them both to inform the estimate of the beat based on the same thing. And so you end up drawing an average. So any of those things can happen.
Yeah, the reason I use auditory and visual though is that maybe it might be worthwhile thinking about like baking an auditory advantage into weighting your model.
Yeah.
When you're getting a
So there's
naturalistic-
the parameter of the precision of our expectations will do that. We'll give you, you know, if I set that to be more precise, which of course, you know, our auditory timing is more
auditory,
precise, then it ends up weighting the auditory stream more heavily in terms of our percept.
Well, thank you. Unfortunately, that's all the time we have for questions. So let's thank Dr. Cannon.